transverse waves have crests and troughs. Longitudinal waves have crests and troughs too, but they have special names. Compressions are what we call the crests of a longitudinal wave. Compressions are where the molecules are squished together. They're high pressure areas. Okay, so you remember, longitudinal wave is a shock wave that travels through material. Well, where the molecules are squished together, we call compressions. And right after a crest on a transverse wave, you get a trough. Right after a compression on a longitudinal wave, you get a thing called a rarefaction. Not fraction, rarefaction. Yeah, like, are you a member of his faction? It's like a chunk, it's a rare chunk. So you can see in our little animation, the molecules are just moving back and forth, but where they are piled up, that's a compression. You can see the compression move through the animation, and following a compression, you get a rarefaction. Now, you can't have a compression without a rarefaction, just like you can't have a crest without a trough. You can't have a rose without a thorn.
I think they bred
It's fun to hear, like, oh, someone's paying attention. Okay. Maybe they actually bred them without it? Oh, no. Okay. Now, we talked about density in longitudinal waves. With a longitudinal wave, density affects speed of sound. Higher density materials, like rock and water, allow the wave energy to travel faster than lower density materials, like air. Okay. Foam is really good at keeping sound really slow, because it's got lots of air. Okay. And we talked about the explosion thing. If there was a big explosion, you're going to feel it through the ground first. This is kind of fun. Remember what the speed of sound is in air? Yeah, 340 meters per second. In helium, it's not quite 3 times faster. So quite a bit faster in helium. And in aluminum, it's, 15, 20, almost 18 times faster. So really fast in aluminum. Yay, aluminum. Now, temperature does affect density, but not as profoundly as it affects velocity. So, realizing that as we increase temperature, we do decrease density, but as we increase temperature, we increase molecular motion, so that causes speed of sound to increase. So, as we increase temperature, speed of sound gets faster, and as we increase density, speed of sound gets faster. And realize, in gases, as you increase the pressure, the density does, increase temperature, density does drop, but not as much as it affects the speed of sound. Does this stuff make sense? Hopefully this is, besides the compression and rarefaction, hopefully this is a review. Okay. Give me a thumbs up if you're with me so far. Okay. And we talked about the explosion thing before. If there was an explosion long ways off, then you're going to see it first, because light travels orders of magnitude faster than sound. And then are you going to hear it or feel it first? You're going to feel it in the ground, because that same shock wave that creates a shock wave in air also creates it in the ground, and it's going to travel through the ground faster than it will through the air. Okay, speed of sound. Where do you think the speed of sound is the fastest? Like, where, in what location? Like, if you were to compare Las Vegas to San Francisco, where would you say the speed of sound is fastest? Closer to sea level. So, the speed of sound is going to be fastest when you have more air on top of you, closer to sea level in San Francisco. And if your pilot tells you, we're going to be traveling about 680 miles per hour, just under the speed of sound, be worried, because the speed of sound changes as the plane rises. As the plane rises from where we are now, at 2,200 feet, to where the plane's going at 30,000 feet, the speed of sound is going to drop. He could actually break the sound barrier as he rises. He won't. They can't. Well, at least not, they can't survive it. And we talked about this and this. Okay. Sound pressure. There's a lot of information up here. Let me break it down for you first. Sound pressure is given to you an intensity, and it's a watt per a square meter. Power over area. Okay? Now realize energy divided by time is power. Remember this? So a joule per second is a watt. Energy divided by time is power. Now, sound waves are carrying energy. And how fast that energy penetrates a plane is intensity. Okay? So how fast energy moves is power. Energy divided by time is power. How fast that energy penetrates an imaginary plane, that is a square, that's a square plane, square meter, how fast it penetrates that plane with how much energy is intensity. So intensity is given the unit of a watt per square meter. Yeah.
So what is that next to the PA? Like what is it equal?
So intensity is pressure over area,
Oh, okay.
which is watt over square meter. And the decibel scale is a logarithmic scale. I apologize ahead of time. They didn't set it up like the Richter scale or the pH scale, where it's 1, 2, 3, 4, 5. They decided to multiply everything by 10. They thought, well, it's the decibel scale, which literally means tens of bells, named after Alexander Graham Bell. So they said, hey, let's make it 10 steps of 10. 10 steps. Great. So it's still a logarithmic scale, though. By going from 20 to 30, one step on the decibel scale, you have 10 times more energy, 10 times more power. By going from 2 steps, from 20 to 40, you have 100 times more power. If you remember your chemistry, the pH scale works this way. From 8 to 9, there's 10 times the concentration. And then the Richter scale works this way. From 6 to 7, there's 10 times the earthquake power. So decibel scale works this way as well. Every step is a 10 times more energy step. But unfortunately, they multiplied it by 10. So a step is from 30 to 40. 2 steps is from 40 to 60. So a sound that is rated at 90 decibels has 1,000 times the energy than a sound rated at 60. Because that's 3 steps of 10. 10, 100, 1,000. Does that make sense? This is probably the most succinctly I've ever explained it. I've always had trouble with this whole decibel thing. That if somebody says, well, if you have something at 110 decibels, how much more power does it have versus 100? It has 10 times more. How much more power does 110 decibels have versus 90 decibels? 100 times. Agreed, Griggs? Agreed? Okay. Now, sound intensity is really interesting because when you look at a sound wave, it's a shock wave that travels through how many dimensions? Okay, I'm clapping like this. Did you hear it that way? Okay, I'm going to clap it. You won't be able to hear it because sound only goes in one dimension. So you couldn't hear it, right? You couldn't hear it? Yeah, it travels in all dimensions. So sound waves that go out travel in all dimensions. So if you want to know how their intensity falls off with a single dimension, it falls off varying with the other 2 dimensions. So in other words, if you look at a sound wave and you have a certain sound, you're 1 meter away, if you double your distance, double your x, it falls off with the y and z dimensions. So intensity falls off with the square of distance. This is called the inverse square law. Intensity varies with 1 over the square of distance. Distance is 1 dimension. So if you're looking at how something falls off with 1 dimension, it falls off with the inverse of the other 2 dimensions. So if you're going from 1x to 2x away, then it's going to fall off with 1 over a y at a z, the other two dimensions. Does that idea make sense?
So the R is assuming that it's traveling in a circle, right?
Yes, exactly. So it's kind of like this. The wave energy that my clap makes isn't lost, but it's distributed through 3 dimensions. So if you're really close to something, if you reduce the distance by a half, then it loses less energy. Right? If I go from here to here, it loses less energy in the y and z dimensions. Does that make sense? Okay. So almost everything does. Almost everything that propagates through 3 dimensions will fall off with the square of distance. The inverse square law shows up all the time. It's going to show up with light intensity too, because light also propagates in 3 dimensions. So light intensity will also fall off with the square of distance. Okay, so I think I covered everything I needed to cover. This is actually kind of interesting. You can have negative decibels below the threshold of hearing. This scale was just scaled to you and I 100 years ago. And the threshold of pain used to be up at 100, and then they started pushing it down. Now it's down at 120. Some of you will still feel pain at 100. Some of you have so destroyed your hearing that you won't even feel pain at 120. Because you're like, whoa! I like the earbuds and bounce sound back and forth on my eardrum. We'll talk about earbuds next time. Yeah.
So, how many decibels does it take to blow out eardrums?
Depends on each person. Toddler, probably 100. You and I, probably 120, 130. Yeah. Your brain is basically calibrated to say, something's wrong, and that's when you start feeling pain. Before, like, how much force does it take to break your bone? You're going to feel pain before it actually breaks, kind of like that. But you'll feel pain before it breaks. So it depends on each person. Each person has different ears. Doppler effect. Okay. Consider this. If I can clap and then run really fast and clap again, is it possible that I could run so fast I could get to my original clap and make another clap? So you wouldn't hear, if I'm running towards you really fast, I'm clapping right behind the original clap, the last clap. What you're going to hear instead is, as I get closer to you, right? And if I'm running away from you, you're not going to hear, you're going to hear. Does that make sense? Here's another analogy. Imagine you can swim so fast you can catch up to the wave you made. So if you did a butterfly, splash, and you swam and then make another splash, the splashes are going to get closer together in the direction you're moving, right? And they're going to get further away in the opposite direction, right? That's the Doppler effect. When a sound source is moving, the sounds it makes, the crests get closer together in the direction it's moving. And the sounds it makes in the direction it's moving away, the crests get further away. So it sounds like the frequency is higher when something's moving towards you and lower when something's moving away. Okay, who stole my buzzer? Now, this used to be glued together, and it's not glued together anymore. And the effect is far more pronounced outside, but we're not going outside. But I'm going to stand over here so I don't hit anybody. But see if you can notice the Doppler effect when I spin this. Can you notice that?
Yeah.
I can't because it's basically the same distance from my head the entire time, so it's never really moving away or towards. But hopefully it's pronounced enough that you can hear it move towards you and away from you. And it's not just the volume. Hopefully, as something moves towards you, you hear a higher pitch. And when something moves away from you, you hear a lower pitch. That's Doppler effect. Let's get through this. Okay. What sound does a race car make? That, right? You ask any toddler what sound a race car makes, and they always give you 2 syllables. They give you, yeah, near oo, near ow, or ver Like, my 2-year-old knows this. He goes, vroom, you know, and like sounds, all kids know this, that sounds go ver because when something moves towards you, it's a higher pitch. When something moves away from you, it's a lower pitch. I got this sound. I didn't even search for race car or Doppler effect. All I searched for was car passing. And that's what I got, that because when you're moving towards a sound source, or a sound source is moving towards you, the pitch will be higher. When you're moving away from a sound source, or a sound source is moving away from you, the pitch will be lower. Is the pitch of the wave actually different? No. Exactly. Yeah, exactly right. It's just your perception of it. So the sound waves appear to be higher in pitch. They appear to be lower in pitch. The waves haven't changed. It's just you are getting closer to the crests. If it's moving towards you or you're moving towards it, the crests are closer together. Now this phenomenon also happens in light, but it has a special name when it happens in light. And you have to think about objects moving really, really, really fast for it to affect light. Stars, galaxies. But for sound, a little beeper swinging around is close enough to change the pitch to the point where you can notice it. Gesundheit. Now, back to our swimming analogy, or swimming idea. Imagine you could swim so fast, you can swim as fast as the waves in the water. So you make a splash, splash. And you're swimming so fast that the next splash is right where the last splash was. Splash. And you're still swimming, and you make a third splash. What's going to happen to that wave? It's going to get huge. And that's what happens in real life. You keep going, and you keep getting closer and closer to the last wave you made, and eventually they pile up. So imagine this is an aircraft just sitting on the tarmac. Rum, 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 rum. When it starts going, it starts catching up with its sound. This is you not being able to swim fast enough to the wave. But what happens when you're actually able to swim as fast as the waves moving away from you, or a plane is able to fly as fast as the waves moving away? This happens. This happens. What is this? Yes, it's a plane. So what is this right here? It's a cloud. Clouds form in high pressure or low pressure? It's a beautiful day today. There's no clouds. It's high pressure. When it's low pressure, then we get lots of clouds. This is a low pressure cloud. A low pressure zone is called what in the longitudinal wave? A rarefaction. This is a huge rarefaction. So when a sound wave is made, a compression is created, and if you can catch up to the next compression and make another one right on top of it, another one right on top of that, another one right on top of that, another one right on top of that, all those compressions pile up. And that's what happens when you break the sound barrier. So this is a diagram of an F-14 breaking the sound barrier. Can you see the compressions piled up? They're right there and right there. Can you see the rarefaction behind the compressions? Yes. You can see the clouds from the rarefaction that is created behind the compressions, but you actually can't see the compressions. Let's see if the video is going to run for me. This is an F-14 flying past an aircraft carrier and a bunch of soon-to-be deaf sailors. Breaking the sound barrier it goes. So he actually breaks it twice. He hits it and then he hits it again. And what's really slick about this, there are physicists that can use this angle to determine exactly how fast he's going. Or she. Yeah, it's just basic. Exactly, it's just basic trigonometry and geometry. So, if this is what it looks like when you are just standing still, And this is what it looks like when you're moving. This is what it looks like when you're moving equal to the speed of sound. Yeah. We don't know yet. Because then quantum effects kick in if you break the light barrier. You would never even get there, and we can talk about that next time. Yeah. Good question. Because all of these compressions have piled up. Imagine someone claps. Now imagine 1,000 people all clapping at the exact same time in the exact same place. That's what's happening. The compressions are piling up. And this is what it looks like when you break the sound barrier. Yes?
If like 1 million people did this at the same time, would it make a noise or would it still be quiet?
Probably be still pretty quiet.
Dang it.
Keep in mind, they would all, yeah, anyway, this is called a Mach cone. This wave of high pressure compressions that the plane drags behind it is called a Mach cone, named after Ernest Mach. For some reason, it's not, yeah, anyway, there you go, that's the Mach cone. This is a pressure diagram of a bullet. Bullets do travel faster than the speed of sound. This is kind of cool. Does anyone know what this back here is? It's extremely low pressure. It's called cavitation. Cavitation occurs when the air is basically pushed out of the way and air can't get back fast enough. It's massively destructive. And then here's more waves of an aircraft. Looks like an SR-71. So the sound barrier was broken originally the first time by Chuck Yeager in an X-plane. Experimental plane was designed just before breaking the sound barrier. And what he reported, this is like 1950s-ish, what he reported is when he was traveling through the sound barrier, he hit a tremendous amount of turbulence. Why? And what are the waves? They're compressions of air. What happens when you compress gases? What happens to their density? They get denser. So he was cruising along, and the faster he went, the closer he got to the sound barrier, the more dense that air was they had to punch through. The great thing is once he punched through, it became very, very smooth. He had no more sound, he had no more compressions to fly through. It became very, very smooth. But not originally. When he originally had to punch through it, it was like he was flying through water at that instant. It was such high pressure. Okay, I have something for you. When we start next time, we're going to learn about mechanical resonance. Mechanical resonance is what happens when you cause things to vibrate at their natural frequency. I'm going to leave these up here for a little bit. This is just a stick of aluminum, which just happens to be 2 feet long. So I'm going to hold it right at the 12 centimeter mark. Then up here I have some crushed bow rosin, just like one would put on their bow as they drag it across strings. And this is what happens. Actually, when I have more bow rosin, this is what happens. I've caused the rod to vibrate, and it just happens to vibrate with a natural frequency. Now I'm holding it right in the middle of the rod. Watch what happens when I hold it anywhere else. Maybe I hold it up here. Or if I hold it up here. But if I hold it right in the middle, or right in the middle of the middle, so
is that the same principle like the tuning fork?
no.
No?
Well, yes and no.